Welcome everyone to this SPHN training session on a first introduction to RDF and SPARQL. And I would like to introduce you to our today's speaker, which is Vasundra Touré and Philip Kraus. Both of them work very heavily on the development of the RDF schema and of the whole RDF endeavor within SPHN. And I think they would like to give you today like a first glance on what is RDF and how can it be used in the context of SPHN. And with that, I would like to give the floor directly to our speakers.
Yeah, thank you, Sabine, for the nice introduction, and welcome everybody. And we have actually a quite short agenda for today, but actually a packed 1 hour. So first, I want to just give you a quick introduction about the strategy. So why RDF and how does it look like and what is all the things about? And why do we do a, let's say, surface scratching in this first training primer, as we called it? And then we will go through the main components that we actually use in SPHN. So which is the ontology, where we start from. Then we will go over RDF itself, and then also how to query the actual data using SPARQL. And why actually are we doing that one? And probably all of you are familiar with the FAIR principles. And FAIR is good, but sometimes you also need a little bit more. And we restricted here to really the 3 key points that we will really want from that whole system. What we actually need is something, we want to describe the data as it is. So we want to really formally describe the data as it is, but sometimes we want to allow certain levels of freedom. And also we don't want to be limited by something like a table, because sometimes you need more than one relation that is possible, and relations have a meaning. And this is given to us by the use of ontologies. The next one, where we pick the accessibility from FAIR, is actually the data that we encode. So the clinical data that we encode is information, and this should be stored and queried using open formats. And very important, it should mean the same thing in 10 years or even more on the horizon. So we want to store it and query it in a format that is open and is a really open standard also to retrieve the information. The next one is the interoperability, where we actually have really high constraints on the foundation system, because we can't assure that actually all the hospitals are using the same database system or something else. So actually all this information can be created, stored, exchanged, merged, read, and queried by different systems. And in all cases, I want that all the information that the researcher takes out of that data has always the same meaning. So it leads to the same information for the researcher. And also I want that every bit of information that is described as the same thing, I can formally describe it as being the same thing, so that the machine knows that it's the same. You can think of 2 hospitals describing a disease, that this is the same disease, so they should describe it the same way, and that the researcher does not need to deassemble that one. And also what is really crucial here is also I want to make use of the information that is already available. Just think of ICD-10 or SNOMED vocabularies. And this interoperability is given by the whole semantic web stack. What is that semantic web? And probably you have seen that slide, or at least that man on the top right, which is Sir Tim Berners-Lee. And actually he founded is an inventor of that World Wide Web, but also the RDF or semantic web. And the idea is here that, and it's transferable to our scenario here in SPHN, you have a decentralized amount of decentralized producers of data, and also decentralized consumers of data. And sometimes two producers means the same thing, and for a consumer, it should also look like the same thing. And whether the consumer is a human, which is the highest form of intelligence currently, can disambiguate that information, also a computer should do. And that's also what he encodes into the web. But how does that look like? And there is a quite old, very basic picture. It's called the semantic web layer cake. And we don't want to go through all of it, but let's just remove everything that we don't cover. What we will also cover today is actually ontologies, RDF and SPARQL, where we will transform, or we will go through that semantic web layer cake from the top. So we first will cover ontologies and taxonomies. We will also cover the RDF part, actually how to encode data or how to encode information. And then we will also how to touch the SPARQL part, how to retrieve information from that encoded information. First, we will go to the ontologies. And what is actually that ontology? And we will definitely look at one standard. It's the OWL standard. It stands for OWL, Ontology Web Language. It's a W3C standard, so from the World Wide Web Consortium. And let's rephrase that one in one simple sentence. It's how to formally describe meaning of information. And so that's actually solving our, we want to model something, but leave out a little bit of freedom. And how do we model that one? And I said in the beginning that we want to don't want to be restricted by tables. Why do we don't want to be restricted by tables? It's because we typically want to model ontologies. And if you, for example, think of a vocabulary, that's just a glossary of terms. So maybe the basic Duden is this one. There exists a next level of description power. It's called the thesaurus, which actually holds also synonyms. So some or the more advanced students also hold that synonyms. So that's the see also stuff. But both of them are actually not sufficient for our needs. More important is taxonomies, which have more power. It's also hierarchical trees. And a prominent example here is ICD-10, which can model like families of indications and their subfamilies. And even more power comes with using ontologies, which says that some diseases or some statements are actually can be in multiple parts of the hierarchy and still are the same thing. So whenever you have cross-references inside the hierarchy or links between hierarchies, then you have, or then you need an ontology. And actually that's what we need. So in short form, an ontology is actually descriptions and rules, how a thing is connected to another thing. It's quite similar to a table definition or a more database schema definition, but actually using a graph-like representation. And it can do a formal interpretation of a thing, but it does not have to actually, or it doesn't need to actually model the whole world or even everything. It can leave out things by intent. And for everybody who's more familiar with relational databases, the ontology can be somehow compared to an entity relationship model. Of course, you need more extensions and things like that, but it has some elements from there, and we will see it later. And there's the SPHN ontology that we can use for viewing that one. And this one is now, I opened the SPHN ontology in a desktop tool called Protégé. There also exist other tools, but Protégé is the most prominent open source one. This is our current release version that we can browse to actually encode information. So the idea is here, I just need to click on entities. So as you see here on the top left, we actually have a class hierarchy browser. It's a little bit misleading because the classes are actually not a hierarchy, but they are mapped to a hierarchy. So because they're easier browsable. And let's just pick the element of the allergy. So here we have different classes or concepts actually that form a hierarchy. And these allergy, for example, in the lower part, you see here different predicates. So for example, I can state that my allergy here is equivalent to something else. I can also model it as a subclass of, so this is where the hierarchy part comes in. But I also can say it's subclass of something else, which we will not cover today, but later. We also have the annotations part. So I can say that this allergy, what I mean here, has a label called allergy, which is obvious for us. And we have also a comment, so risk of harmful or undesirable physiological response, which is unique to an individual and associated with exposure to a substance. So that's what we mean with that allergy. And how do we use it? And where we go to the usage tab, and there we have actually quite an extensive list of things, what we do. And as you probably know, that an allergy is typically associated with a human, or in our case, we make studies about humans. We also need to connect the allergy to a human. And where we can scroll down and we find the has subject pseudo identifier, which actually means, because in our case, we don't model the human directly, but a pseudonymized identifier of that human. I can connect the allergy with a has subject pseudo identifier to actually the pseudo identifier. And we can browse that one. So we just remember the has subject pseudo identifier. We go to the properties and see that there we have the has subject pseudo identifier. And here in the annotations tab, we see that in the domain, which means where can I use actually the has subject pseudo identifier as a property? It's quite a lot of concepts listed, and it always points to, so that the range means pointing to a subject pseudo identifier. If we go back to the classes, so especially our allergy class, we know now that we can model that allergy towards a human or a pseudo identifier. But now we also want to model a certain substance to the allergy, because the human typically does not only have an allergy against everything or whatever, but also against a certain substance. And here we find also the property has substance. So we can use a substance, hook it up to the allergy, which hooks up to the person or the individual. And this is actually how you build or encode the data that you mean using an ontology. How the ontology describes how the data is connected. Okay. What actually can we learn from that allergy definition? So we have seen that it is connected to a patient, or that was what we meant by a patient, using the has subject pseudo identifier relation. What I didn't show is that we connect to a hospital using the has data provider institute relation or property. We use that terms synonymously through the presentation. And actually, this allergy is also connected to a substance using the has substance relation. And substances are defined in SPHN are the same as substances as described in SNOMED. We can quickly go back to that definition. And what this ontology does not say anything about is about serialization, data types, cardinalities, file formats, or anything else. So actually, we leave that one really open. One thing I promised to go back from the allergy to see the substances are defined as the same substances that are described in SNOMED. So we can actually go to the substance. I need to scroll down a little bit to the substance. And here we have, and you might see it, it's on dark gray, on light gray, which is not so very good contrast. You see it has the URL HTTPS biomed ch RDF SPHN ontology SPHN substance. And we model it as being equivalent to something else called substance, which is for the human reader a little bit misleading. But if we click on it, we are also browsing to that same thing. And we say our substance, or the SPHN substance, is the same thing as this substance, which just takes a little bit of time to load. Okay. Now it loads. So what you actually saw that the usage actually changed a lot. So there's enormous amount of usages for the substance. But what is really interesting is that actually the URL changed at the top. So I changed to snowmat.info ID 105 something else. And that's what we meant. We want to use information that is already there. So the SPHN ontology declares our own substance. But we state that our own substance, what we mean with the substance, is actually really equivalent to the substance that SNOMED is modeling. And we also see that here now the substance is just an English language tag, and all the information that SNOMED actually provides about substances are already there. Okay. And so for also the more the database, relational database people out there, so you can now think of an entity relationship model that looks a little bit like this one. So we say that actually the allergy is there. The allergy has an RI, or what will be that, Vasundhara will explain shortly. And there will be some relations or properties leading to something else. So for example, the has subject pseudo identifier leads us to a subject pseudo identifier. The has data provider institute leads us to a data provider institute, and the has substance leads us to a peanut substance. So quite similar to a relational model, but actually just think of transported the basic idea to a graph. So now we've talked a little bit about ontologies, but there's also instance data available, and most of you will typically always have instance data at their hands. So what's the difference? The ontology actually describes how objects relate to each other. They formalize the meaning. It's stored in typically RDF or OWL, doesn't have to be. And is in SPHN actually, SPHN provides the ontology, but it can be adapted by projects. And sometimes you will hear SPHN also call it SPHN RDF schema. What we mean is the ontology. And these are actually the red circles at the top that you see, and they're connected as you have seen with these blue lines. There's also instance data. And actually you have seen that we have modeled an allergy and a person and things like that, but that's just abstract things. You also want to, or you need individual, especially encoded in the data. That's what we call instance data. It instantiates objects from the ontology. They are modeled according to the ontology. And in SPHN, it's that what hospitals actually produce according to the ontology, and they store it in RDF, and it's transferred to the project environment. And these are the circles here in this blue. And there you see also some dashed lines that connect actually the instance data with the ontology. And what these means, you will see in a few slides, where actually Vasundhara will take over to explain you the instance data encoded in RDF.
Thank you, Philip. So now let's focus on the RDF part. So RDF stands for Resource Description Framework. It's a W3C standard as well that has been published for the first time in 2004, actually. And it has been used in several projects in many fields for representing and exchanging information. So you may be all, or some of you may be familiar with table representation of data to express information, as Philip already mentioned it before, where you will have columns that are actually representing types of data, and the rows will be the instances of the data. In this example, we have two different tables, and we have one instance data that is allergy1, that is an instance of allergy. We also know here that allergy1 has substance peanuts, and peanuts is actually an instance of the peanuts substance table. So there is a linkage that is done here. We can also represent this knowledge simply with graphs. And the most atomic level of information that you can have in a graph is actually a binary interaction. And in RDF, we decompose these binary interactions with 3 elements. So we have the subject here represented with the allergy 1. The subject is basically identifying the element that we are describing in this interaction. Then we have the predicate that is connected to that subject. So here it's called has substance. And sorry about the noise, if you can hear it. And so the predicate is, or the property is usually describing the type of information that we learn about the subject. And finally, the third element that we have is an object. And the object is the actual value of the information that is described about the subject. So simply, if we would like to put this example into English word, we can say that this data is representing an allergy to the substance peanuts. So now in RDF, we have 3 different types of elements that we can use to build those graphs and represent those binary interactions. The first element is what is called IRI, or International Resource Identifier. As you can see in this second column, you have an example, and this is basically a link. And this is an ID that is used. And you are probably familiar with links that you use, in web browsers, where you put a link, you click enter, and then you get some content and metadata associated to it. So these are valid links, but IRIs can also be links that are not resolvable, meaning that you define those IRIs in a specific RDF document, but it will not necessarily lead to something on a web browser. So these are elements that we can use. Yes, and I forgot to mention that IRIs are a bit more generic form than URIs, in the sense that you have more character sets that you can use in there. Then the second type of element that we can use are literals. So literals are basically describing a specific element. So in this example, we have the description of a peanut. And with literals, we use the XML schema namespace to tell us what type of information that we have here. So the peanut here is actually a string. And with the XML schema, you can define other types of elements like integer, or if you want to specify a date, you can also have this type of tags that enables to annotate this information. And finally, we have blank nodes. So blank nodes are keys that we can define inside a data, and this blank node will only be valid inside that data. So in our case, we would suggest, for the sake of this introductory training, that we do not focus too much on this. And also in the context of SPHN, we are not using blank nodes, because there are some tricks to do to be able to query them, and it's a bit more complicated than just using the IRIs and literals, which are sufficient for our use cases. So now that we know the types of elements that we can have in RDF, how do we combine them with this atomic structure that I presented you before? So this subject, predicate, object, which also is called a triple in RDF. So this triple of information. In the case of a subject, you can either have an IRI or a blank node. In the case of a predicate, it's only an IRI that can be used. And if you observe here, we are using the has substance coming from the SPHN ontology that Philip has presented before. And we are reusing that link. And for the object, you can either use an IRI and refer to another RDF element. You can use blank nodes or literals that are defined on the go. If you want to know more information about these specificities, there are nice documentations that are provided, so you can just have a go through it. So now that we have all the structure, you may be wondering, okay, when I have my data, do I really need to write down all the IRIs every time? You know, here we only have one example, but in your data, you will have thousands, billions of nodes. So in order to avoid having this explosion of links, there are namespaces that we can define. So what is a namespace? It's a mapping that connects a particular prefix to a URI, and that allows us for a more convenient and human readable rendering of the RDF. So what I mean by that is that this is the example we had before, right? We had the subject allergy one with the full IRI identifying uniquely this element. We had the has substance and the peanuts with the full IRI. What we can do in our data file is to define those prefixes. So here we choose to have substances to represent the http://sib.swiss/substances. And then in the rest of our data, we can reuse substances whenever we want to refer to that IRI. So this is what you observe here on the bottom right. Substances, peanuts is equivalent to this. And we have done the same for the SPHN ontology. So we define the SPHN prefix, and this is referring to the biomedit.ch/RDF, etc. So here, later on the data, you can simply have SPHN has substance to refer to this property. But you don't have to do it. I mean, if you want to mix and match, you can also just keep the IRIs for some of them. This line and this fourth line are basically the same, but represented with different sentences. So just a point, not all RDF formats support this namespacing, but Turtle, which is one of the main format that we use in SPHN, does. Okay, so now we have the elements to model our data in RDF, and we know how to do it. So let's just do an example. We want to model, according to the SPHN ontology, a patient that we call Anonymous 1 that came to our hospital, Hospital 1, and Anonymous 1 actually has an allergy against peanuts. We know that peanuts are a substance, and we also want to declare or link our peanut substance as an instance of SNOMED CT. So basically just saying that this peanut is corresponding to that SNOMED code. So what do we do first? We just need to look at the SPHN ontology to make sure that the model that we will be building complies with the schema that is provided to us. So Philip has shown it to you before already, so I will not go too much into details, but the concepts or the classes that are of interest for us here are allergy. We also have the data provider institute for representing the hospital. We also have the subject pseudo identifier for the anonymous one, the patient, and the substance. So all the elements are there that we need to model. And when we look more closely at the ontology, this was already shown before, the allergy seems to be the central point of the schema, because it connects to the person via the has subject pseudo identifier property. It also connects to the hospital via the has data provider institute property, and it also connects to the substance via the has substance property. So what we do first is that we create IRIs for the instances or the data that we want to model. So the instance data that we have are the anonymous one, the patient, the hospital one, which is the specific hospital we're going to, the allergy one, and the peanuts one. And for that, we define those IRIs, and you can see that here we have an IRI or a resource of fictive patients, and there I have my anonymous one patient. I also maybe have a resource for allergies, and there I have my specific allergy that I'm referring to here in this data. So now we have the classes, the instances. What is it that we are missing now? What is the next step that you would do? And I would like to invite you to use the chat if you have any ideas.
It seems that currently people are struggling with using the chat.
Okay, that's fine.
Or
just move to the next
slide, opening.
So. Yes, okay, so what we need next is to make our connections. So we have our instances, but they're just out in the blue like this. They're not connected to anything. So we need our predicates. And we are reusing the predicates from the SPHN ontology because this is what we would like to represent. And we have the has substance, has subject pseudo identifier, has data provider institute, and the IRIs are based on the what the SPHN ontology gives us. So now we have our instances, we have IRIs for our instances, and we also have our predicates connecting those instances. But we're still missing something to be completely clear on the data. What could that be? So it's actually the semantics types. So when we instantiate our data, anonymous one, hospital one, allergy one, peanut one, we need to know what do they actually correspond to. We don't know what are their types. I mean, intuitively with the human brain, we can reason that, okay, anonymous one may be the patient, but in the data here, if you're giving that to a computer, she doesn't know what it means. So for providing the semantic types, we have this RDF type that we use. And this is another connections that we will do to the instances. And this is actually the dashed line that you saw earlier, where Philip was showing you the ontology on top, the SPHN schema. At the bottom, you had the data instances, and then you had the link from the instances to the data schema, to the schema. So when we put everything together, this is what we obtain as a table and as a semi-graph. So we have our data instances for anonymous one, hospital, allergy, peanuts. We know that anonymous one is actually a subject pseudo identifier. So this is described with this relationship. Hospital one is of type data provider institute, and so on. We also have our predicates that will connect our instances together. And then the last step would be to put that into a valid RDF format. Turtle is one example that we use, and this is how a turtle file looks like. If you decompose it, you have on top the prefixes that define the different namespaces that you can use. So for example, we choose to have allergies for the siv.switch/allergies IRIs. And then below that, we have the different data instances connected to their type. So anonymous one is of type subject pseudo identifier. And on the right side, you can see how that looks like in a visual representation. Hospital one is of type data provider institute. Allergy one is of type allergy. And then the substance is peanuts is of type SNOMED. So here we are connecting to an external ontology. This is not only from the SPHN. This is using the SNOMED content. Then finally, we have the relations to the allergy. As we have seen, the SPHN schema puts the allergy as a central point, and we just propagate the relations that we need. So we need to connect the allergy to the subject pseudo identifier, which is anonymous one. This is the link that you have here. Then the allergy is connected to the data provider institute, which is hospital one that you have here. And then allergy one has a substance peanut. And then you can, from this, build up more and more, integrate more and more information into it. And this is the beauty of the graphs that you have. You can just use the schema, the content that is provided with the schema, and then add more and more data to it. So now, once you have modeled your data, it's also nice to explore it and have more insights to it, right? So I would like to give the word now back to Philip for showing you how you can load the data into graph databases.
Thank you. Okay, so how to load actually the data into a database, and there's special databases for that one. And these databases are called triplestores because these RDF that Vasundhara showed before is actually triple subject predicate object, which triple store as a sensible name. And in the slides, we have some backups as well. So I will do it live, but you will have all the steps as screenshots with arrows in the slides. And there exist quite some different triple stores inside this whole universe. And namely, you will find from AWS, it's a cloud solution, but all of the others are actually on-premise or hybrid solutions. And for the example, we will use GraphDB on the top right. And if you also want to play around, there exists a SPARQL playground that you can use from SIB. We will probably post a link later in the chat. And open source ones like RDF4J or Apache Jena that you can use. Just for the sake of completeness, or the examples here are just examples. There exist some more. I just picked randomly some larger ones. Yeah, we will go to the example. I will just open this one here. So we will use the example of GraphDB, and I already created the database called SPHN demo. And so in the repositories, you can create a new repository. So this is like a schema for the relational database people, where we can give the something useful name. Let's call it or SPHN demo 2. And you can leave actually everything where it is and just click create. I will just use my old SPHN demo instead of using the newly created because I preloaded some data. And we are getting to import the data that Vasundhara just modeled with you. So we're clicking on import RDF. And here you will see two main tabs. So the user data is actually what you can upload. You can download from a URL or import a text snippet that we will use now. But you also can use server files actually where you have maybe something on some disk where the server is running. And there exist other possibilities. We're just using now the most simplest one that is working for our demo. Just copying the data that Vasundhara just used. So actually that's really the same that you've seen on the slide before. I click import, I click again import, I just pick the standard stuff. And now it's doing the import. It says it's imported it. And as now you know, okay, we have that LRG1. We also want to now show how it looks like as a graph. Now we modeled it as let's say text. And we make make use of GraphDB in this case, that we use the autocomplete feature and build an autocomplete index. That's taking a little bit of time. So I click it now because I preloaded some data. And so this is a little bit different from triple store to triple store. Some triple stores, for example, have such autocomplete indexes, which means they index all the resources so that you can query them faster. And we will use that one to use the graphical interface of GraphDB actually to show what we've just modeled. And in the meantime, I will also explain what I loaded in parallel to it. So in parallel, I loaded the whole SPHN ontology, including all referenced other terminologies. So, and this is why it's taking some time, because all the other reference terminologies have some substantial size. Okay. So now we are connected to the SPHN demo repository. And inside the demo repository, you have different graphs. And as if you might remember, I just loaded it to the default graph. So my current data will be in the default graph. And I also loaded in here, used the SIPs with demo ontologies graph actually to load all the other stuff. This now should be ready or not. I'm just clicking on autocomplete. It's still running. Okay. Now it's ready. I can now click on Visual Graph. And Visual Graph is actually an interface in the GraphDB database that allows you to search by names or by parts of the IRI for certain resources. So for example, I'm searching for my allergy 1 that I have, and I will find it by its IRI, so SIPS with allergies allergy 1. And I can click on that one. And this is what actually the graph that we just modeled just looks like. So as you might remember, our allergy 1 connects with the hospital 1 as Has Data Provider Institute. It connects with the anonymous 1 via the Has subject pseudo identifier, and connects with the peanuts 1 using the Has substance. And all of the steps you will find also here in the slides. I will quickly go through. Okay, just some information. I loaded the ontology beforehand, and actually we've just shown it on a nearly fresh GraphDB instance. And it's just for testing because that one was running locally. If you're interested in using GraphDB, you can have a look at the documentation of the database. The link is in the slides, but you will also find it on using Google or whatever search engine you like. Principally, this one was using the GraphDB free version, which is free of use for personal usage. It's not an open source software in this case, and you can apply for a free license using that link. Yeah. So now we encoded data actually in RDF, or information in RDF, and now we actually really do want to get out the information back, right? Rather than doing analysis. So multiple hospitals actually produce data, send it to you, to your workspace, you load it into a triple store, and now you need to get or have questions on top of that information. And SPARQL is there to help you, and SPARQL is a reverse acronym for SPARQL Protocol and RDF Query Language, and it's also a W3C standard, and you can just say it's how to query information. The SPARQL syntax really borrows elements from RDF and also is very similar to actually SQL, a structured query language. So you have prefixes like you have in Turtle or in RDF. Then you have some select statement from and from name we just skip for now, which is defining a special data set. And the where part is actually really important. So where you actually apply graph patterns. We will see in a minute how that looks like. And then you have like typical structured query language elements like ordering, having rules or grouping, limiting, offset, and things like that that you want to use to restructure your data set or your result set. So how does that actually look like? And I just make an example query at the top that's actually working. So here I have the same 3 prefixes we also used for modeling or writing up the RDF in Turtle. It's slightly different syntax, so it's not an at prefix, it's just prefix. And yeah, so, but it's the same one. And the name just doesn't matter, it's just for, they don't only matter for actually this execution of this query. So I'm now asking for actually the code of this SNOMED. And so I want to get out this one, this top right SNOMED code. And I can ask that one by starting by applying different triple patterns. So you can really think of, you have that RDF file in triple subject, predicate, object, and you can query also by that triple pattern thing. So that's also why a basic graph pattern is one line in this where statement. So we are saying that's question mark allergy is actually a variable. So I'm matching for anything, and I store that one in the set allergy that has a subject I don't know, and a predicate SPHN has subject pseudo identifier, and an object patients anonymous 1. So actually I'm searching all the subjects that have this relation to an anonymous 1 patient, and I'm storing the subjects. And this subject I also reuse in the second basic graph pattern for the substance, and then should be then at the substance. And for the substance, I ask for the instance RDF type, and that's my code variable. And how does that look like in an example query evaluation? So the first basic graph pattern actually matches that triple. So and in our example, it only matches this triple. And in our second step, actually, we are appending to that set. So this one is now our variable binding for the allergy, and we follow from that allergy, (allergy variable binding, the hair substance to our peanuts. And in the second, the next one, we are following from that substance variable binding, the RDF type to the code. And finally, we are asking for the code. So we are only retrieving or pushing out information that is bound to that variable (code). And then we just do it live. I just copy the same thing here. So we go to the SPARQL tab. We just copy paste the data, and here we also get some nice syntax highlighting. And then there is the run button on the right one. And then if we run it, we see that there is a result set called code, and where we have our SNOMED code nicely displayed. So we can also retrieve information here. Okay. So a quick test, and similar like Vasundra did, we will just ask for you to provide the answers in the chat, or some hints in the chat. So that was our previous query, actually. And now I'm asking, what do we need to change actually to get the IRI of the hospital, so hospital 1, displayed in our result set? Is there anybody? Okay. No ideas? Or people searching for the chat? So here we have a slide actually that shows our possible relations that we have. So we have 4 relations currently that we are using. That's our graph that we have modeled just before, and for the code. And what we actually do want is, we know that the hospital 1 is actually can be reached directly from the allergy. And our allergy, so we don't need this line anymore. So our allergy actually has an outgoing edge called Health Data Provider Institute, which we just can use. And this will lead us to something like a hospital. So where our hospital 1 is an instance, and just need to reuse also the variable hospital here, because I'm interested in that one. Now we just try whether this query will work. Otherwise, I also have a backup. And has inserted the space. That shouldn't be. Okay. So let's try and run it. And we're retrieving our hospital 1, which is exactly what we wanted. I'm just removing these. Okay. So we did that one as well. Now we have something more fancy, which we don't do as a test, because it might be a little bit tricky to answer that over the chat. So my idea is here actually to query for everything that is below this SNOMED ID. And we can actually ask for that SNOMED ID. Just need to find the no. The SNOMED browser. So that's the official SNOMED browser that you might know. And we are here having the code for the pulse vegetables. And we see that these pulse vegetables, so in German it's Hülsenfrüchte, it's actually every fruit that has something around it. And also here we find that the peanuts are actually a sub-element of pulse vegetables. And actually I want to know, give me all the patients that actually have an allergy against anything in the family of pulse vegetables. And as a human, you know, of course, the peanuts, that's our own, or the patient one, or the anonymous one, that's the only one we modeled. And this one has an allergy against peanuts. And as we have SNOMED CT also included in our data, also the computer is able to guess that one. So if we run that one, our anonymous one is displayed to have an allergy against anything below the subclass or below the family of pulse vegetables, which peanuts is. So the hospitals can actually model the data as precisely as they can or as they know from their diagnosis, and the researcher can choose the level that is appropriate for the research. Okay. So now probably most of you don't do all their machine learning in SPARQL, which is really something very advanced, but you do your slicing and dicing and data preparation in SPARQL to query the data to make it nicely usable for your analysis. So you can probably want to download this in CSV or other file formats. And there exists something, for example, in GraphDB, where you can download it as CSV or JSON or XML if you really like to do that. And if you click on that one, it's downloaded as CSV. And if we want to open that one, there was a question when Excel comes into the play. Now Excel is there. You see that the CSV is actually here. Okay. If you really want to do that on long-running queries, because typically you don't have only one data element, but to actually have all the data of multitude of patients and multitude of hospitals inside, so you have long-running queries. For example, for GraphDB, there exists also a REST API where you can put your SPARQL query as a parameter and then download that one to a machine on long-running queries. The longest one I tested is on a very, very large repository. It was taking, I think, over 40 hours for some export. So this is very stable for very long-running queries if you have an enormous mass of data. So that works as well. Yeah. Some further information. So this was just training primer, as we call it. We could go deeper in all the steps, but not in 1 hour. There's some official references, like the SPARQL reference, that is very helpful. There also exists an RDF primer from the W3C, and also the abstract concepts and abstract syntax one that we linked earlier as well. I can recommend actually 3 books. The one is Bob Ducharme, Learning SPARQL, Querying and Updating with SPARQL 1.1. And there is a second edition that works really well. So that's from O'Reilly, and it has this fish on it. So it's a very good book. There exists a more modern, but really business-focused book for maybe people that are more not only focused on studies. It's from Andreas Blumenauer and Helmut Nagy from the Semantic Web Company in Austria. It's called the Knowledge Graph Cookbook, and you can download it for free after a registration on their website. And there is a, let's say, quite old book from Jeffrey Pollock called Semantic Web for Dummies. It's really all necessary concepts, really, yeah, as the for Dummies books, it's really starting at the beginning, going the whole way through. It's quite old, but still appropriate. What I like really well is some SPARQL cheat sheet that you also find a link here. And there exists a quite lengthy paper on the modern term of knowledge graphs and how it's used. That's linked down there. We want to thank you very much, and we also would like to give your feedback under the link that also Sabine just posted into the chat. So we can collect that and plan for the next session. So there will be some questions about how you perceive this session, and to ask you whether you want to have next sessions and what should be the topics of them. And by that one, I want to thank you all, and I think we can close the recording.